Okay, I'd like to talk about entropy power inequality today. To start with, I need to define what we mean by entropy power. Entropy power of x, some random variable x, is simply equal to 2 to 2hx, where hx is the entropy of x. Now, what's the intuition behind that? Let's consider first x is Gaussian, then hx is just equal to this guy here. Then we'll have sigma x squared, that's the variance of x just equal to 1 over 2 pi e to the 2hx here. And we know that 2 to the 2hx is the entropy of x, entropy power of x. So therefore, like, the sigma x squared is just equal to epx over 2 pi e. So therefore, like, this guy here, epx over 2 pi e, is actually just the variance of the Gaussian random variable that have the same entropy of x. One thing we know is from an information theory class is that Gaussian random variable is kind of special in the sense that, like, it actually has the largest entropy for the fixed variance, or in other words, if we have the fixed amount of entropy, Gaussian random variables will have the smallest variance. So therefore, for any random variable y, we should have epy over 2 pi e. That's the variance of the corresponding Gaussian random variable with the same entropy of y should be less than equal to the variance of y. So, and only when y is Gaussian, these two terms will be equal, right? So therefore, this epy over 2 pi e over variance of y, this ratio, can be interpreted as some kind of measure of how Gaussian the random variable y is. Now, what is entropy power inequalities? It's something very simple. It basically means that, like, if we have two independent random variables x and y, we will have epx plus y is bigger than or equal to epx plus epy. So the proof is not so simple, but it's actually, the intuition is quite elegant. It's just an alternative interpretation of the central limit theorem. Or in other words, if we have several independent random variables, if we add them together, they become more and more Gaussian. So as we just mentioned, we can think of EP, the entropy power of a random variable, over the variance of the random variable as some kind of measure of how Gaussian that random variable is. Remember that a variance is kind of linear when we operate to a sum of two independent random variables. In other words, like, we have variance of x plus y is equal to variance of x plus variance of y. So therefore, we expect that the entropy power applying to the sum of random variables should be superlinear, so that this epx plus y over 2 pi should be longer than this sum of this interval, right? So that the sum will become more Gaussian than the original. And that's basically the intuition behind the entropy power inequality. Now we can write a vector form, or not, a form entropy power inequality for a vector random variable xn. So let's say xn have a covariance matrix sigma square I, where sigma square is the variance of each component. So then we will have the entropy equal to this. We will arrange the term. We have sigma square is equal to this here. So therefore, we can write the entropy power of xn as this one here. So essentially, it's the same as before, only we have over n here. And of course, we will have entropy power inequalities in the same form basically something like EP xn plus yn is bigger than equal to EP xn plus EP yn if xn is and yn are independent. And we can also have a conditional form if we have x and y are conditionally independent given u. The only difference is that we have all this entropy will be replaced by the conditional entropies. And that's it. That's all I want to talk about for